Hi everyone, today I brought a very good question from the topic of Zener diodes and it is from the chapter semiconductors, right? So the question says two Zener diodes A and B having breakdown voltages of 6 volt and 4 volt. Breakdown voltages means Zener voltage are connected as shown in the circuit below. The output voltage V0 variation with input voltage linearly increasing with time. The grammar doesn't seem very right here. What they are basically saying is they want the graph of output voltage with time when input voltage increases linearly with time, and here input voltage is considered to be 0 volt at time t equal to 0. Now before we solve that question, let us first understand how Zener diode is used as a voltage regulator, because that is a crucial part in solving that question. So like any other diode, a Zener diode shown by this diagram has a p side and n side. Now when you apply a reverse bias, which means p is connected to lower potential and n is connected to higher potential. So when we apply a voltage in reverse bias to a Zener diode, initially as the voltage V increases in the negative direction because we are applying reverse voltage. Then initially when the voltage is less than a particular voltage called Zener voltage, this is called Zener voltage. So when the applied voltage across the diode is less than Zener voltage, the current in this part you can see is quite small. So the current is in the Zener diode is approximately 0. However, once the voltage applied to the diode becomes slightly greater than Vz, the Zener voltage. So when you just touch the Zener voltage, the current will rise sharply. So a current will flow through the diode, and remember in reverse bias current flows from N side to P side in the diode, and the voltage across the diode will remain constant at Vz. So this is the main thing about Zener diode which we must remember. Now this state of the Zener diode where no current flows in the Zener diode when the voltage across it is less than Zener voltage, that state is called off state of the diode. And once the Zener diode conducts, the voltage across it remains constant, and that is called the on state. So try to remember this, okay? Now let us try to see how Zener diode is used as a voltage regulator. So let's say you have some load resistance, some device, and you want here exactly 5 volt. However, the problem is your input voltage which you have, this input voltage is, let's say, variable, unregulated. So this input voltage changes with time, whereas you want here constant voltage. Then what you need to do is you need to buy one Zener diode and connect it in parallel to this load such that the P side is connected to the negative of the input so that it is reverse biased. Okay, and then with the help of some resistance here, we connect this to the Zener diode. So this resistance is your RS, let's say. Now, if you want the voltage here to be constant at 5 volt, then you have to get a Zener diode whose Zener voltage is exactly 5 volt. If you want voltage here also equal to 5 volt. Now, how do we make sure that the voltage here remains constant? Well, first what you need to do, the first thing is you remove the diode. So you remove the diode. So if you remove the diode, let's say this is point A, point B. So now calculate what is the voltage between A and B. That voltage will be what? Well, if there is no diode here, then same current will flow everywhere, isn't it? So that voltage here will be from Ohm's law, same as I into R, and R of this is RL. And what will be I? Current will be the applied voltage divided by total resistance of this circuit is Rs plus RL, right? This is your voltage divider formula. So you need to first calculate what is the voltage across the diode when the diode is absent, when the diode is not there. So you have to see that this voltage, if it is less than Vz, okay, then your diode will be off even when you connect it. So even when you connect the diode, it will be in the off state, meaning the voltage across this will not remain constant and the current here will be almost zero, as I told you before, right? So the whole current will go only here. So this would be representing the off state of the diode. And in that case, the voltage here will be basically this itself, isn't it? I into RL. I is the current here, right? And in this case, when your input voltage will increase, this current will increase. As current will increase, this voltage will also increase. So voltage here will not remain constant if the diode is off. But if this voltage is greater than Vz, okay, then if the voltage here is greater than Vz, then we know that the diode will be in what state? On state. So now, though the current here can change, the voltage here cannot change. And this current here I will divide. So let's say here the current is IL and here the current is IZ. So I will be equal to IZ plus IL, and output voltage here will remain constant at Vz. So Vz will be your output voltage here, okay, which is equals to IL into RL. And this input voltage will be equals to voltage here, which is I into Rs, plus voltage here, which is Vz, isn't it? Voltage here remains constant at Vz, I told. When it is in what state? On state. So this applied voltage should be voltage here plus voltage here, right? So in that case, what will be your I? Bring Vz this side, Vi minus Vz by Rs. So now, even if this Vi increases, Vz will not increase. Therefore, this current has to increase. And when this current increases, this Iz increases, but IL should remain constant. Why IL should remain constant? Because your RL is constant. But if you change RL, then IL also has to change because Vz remains constant. So in this problem, if your RL is constant, then you know Vz is constant once your diode is in what state? On state. So IL has to be constant, right? So let me give you a numerical example. Let's say the voltage here should be 5 volt. But let's say I applied 8 volt. Then what will happen? Voltage here must be 3 volt, isn't it? Because 3 volt plus 5 volt will be 8 volt. Later, if this becomes, let's say, 9 volt, then voltage here will not change if you are in this state. Meaning the diode should be working in what region? Reverse breakdown region, right? So if this is 9 volt, then here 5 volt, then here 4 volt should come, which is possible because when voltage increases, this current increases, right? So the voltage here will also increase. So this is how Zener diode is used as a voltage regulator. Now let us consider this circuit and we will assume that there is no resistance here for the time being. In the actual question, there is some resistance here, okay? But we will assume right now it is not there. And we will see how output voltage will change with time. How output voltage will change with time when input voltage increases linearly with time, they told, right? So input voltage increases linearly. Now these two diodes have Zener voltage 4 volt and 6 volt. Now if you look at this circuit as it is, then the output voltage you can see will be exactly same as input voltage because this is a resistance-less wire. Resistance-less wire, no resistance this part has. Similarly, this wire has no resistance. So potential, if this is 0 volt, this is also 0 volt. If this is 2 volt, this is also 2 volt. If this is 3 volt, this is also 3 volt. So output voltage will exactly copy the input voltage. So your answer will be like this, same as input, if it was this circuit. However, none of the options has this one. That means we need to assume that there is some resistance here ourselves. Actually, every source here will have some internal resistance, right? And experimentally speaking, every wire will have some resistance, isn't it? So this is your series resistance which you must assume. Without this, your answer will not come according to what they want. Now, what will happen in this circuit? Let us try to analyze first. You can see first what I need to check, whether these diodes are on or off. And how do I check that? I remove both the diodes, right? And I measure what is the voltage here. So if I remove both the diodes like this, so once we remove these diodes, we have to see what is the voltage across, let's say, these 2 points. So voltage across P and Q will be what? Well, that voltage will be same as this voltage, right? Some current I will flow like this, isn't it? And this is input voltage, so you have to assume some battery here, but that voltage of that should increase linearly, okay? So what will be the voltage here? That will be equals to I into RL, and I will be V input by RS plus RL, isn't it? So this is the voltage between P and Q. Now, if your input voltage is very small, because input voltage starts from 0, remember. So when your input voltage is very small, when input is very small, obviously this voltage between P and Q will be also very small, isn't it? Because this is fraction of this RL divided by RS plus RL. So if this is 1, this is 1, this is 1, then this is 1 by 2. So this voltage will be half of input. So if input is very small, this voltage also will be very, very small. And if that voltage is very small and it is less than the smaller Zener voltage, which was the smaller Zener voltage, the diode here had Zener voltage 4 volt, here it was 6 volt. So if it is less than 4 volt, the smaller Zener voltage, then it means what? Both the diodes are in what state? Off state. Both diodes are in off state. And if both diodes are off, then no current will flow through these diodes. So we can imagine these diodes are not there, like this only. So then in that case, your output voltage will be same as this voltage across P and Q, isn't it? And that voltage will be input RL by RS plus RL. So it will be some fraction of input voltage, right? So as input voltage increases with time from very small value from 0, output voltage will also increase from 0. So output voltage will also initially increase, isn't it? Now, as your input voltage starts increasing, your voltage PQ will also increase, right? And when that voltage will become, when voltage between P and Q becomes greater or slightly greater than your 4 volt, the smaller Zener voltage, then this voltage here will start conducting, right? So now let me show you that diode. So the 4 volt diode will start conducting, isn't it? This diode will not conduct because this diode needs 6 volt, but here the voltage is 4 volt, and once you touch 4 volt, this diode will be on. So 4 volt diode will be on, whereas 6 volt diode will remain off. And once that happens, the voltage across this we know remains constant. So this output voltage will become constant at 4 volt. So this would be the right graph if this was the question, if there was no resistance here. But in this particular question, they have added some resistance here, isn't it? So let's now try to think what will happen if there is some resistance here, okay? Now let's come to the actual question. So if there is a resistance here, remember Zener voltage of this is 4 volt, then what will happen? How will the output voltage across RL change? Well, even now when input voltage is very small, voltage here will be also very small, and if voltage here is very small, if it is less than 4 volt, if I call this point P and this point Q, if voltage across P and Q is less than 4 volt, then obviously both the diodes will be off, and in that case your output voltage here will be the current flowing, which is VI divided by RS plus RL times RL. Let me write this one this way, okay? VI is equals to, let me take this one which is in the numerator, in the denominator of denominator. So this will become RS by RL plus 1. So let me write this way, okay? So now when the voltage between P and Q becomes slightly greater than 4 volt, when it just touches 4 volt, what will happen? This diode will be still off, right? So you can forget about this diode because the voltage is less than the Zener voltage of this. And this diode will become now on, right? It will now work in the reverse breakdown region. So you may think voltage here will remain constant at 4 volt, which is right. But now you cannot say voltage here will be constant, which means output voltage will not be constant now. It will not be constant because you know from the IV graph of Zener diode that when you reach the Zener voltage, the voltage across the diode remains constant, but current increases. So when this voltage will increase with time, the current here will also increase. And as the current here will increase, voltage here will increase. So the overall voltage, which is this voltage plus this voltage, will also increase. So the output voltage here will increase. The only question is whether it will continue with the same slope, or will it come down slightly, or will it go up slightly. The slope will increase or decrease, that we need to check. One simple way to think is, when this R is introduced, then this whole resistance, this branch overall resistance will increase or decrease. Remember, it is in parallel. So the effective resistance of the load, you can see that whatever resistance this voltage will see here, that equivalent resistance has decreased. So your load resistance effective has decreased because of the presence of this R in parallel. And if that decreases, this whole thing will increase. And when this whole thing increases, your output voltage will decrease when your voltage across P and Q just crosses 4 volt. So if it did not cross 4 volt, your output will increase with input according to this equation. Let's say this way, right? But once this starts conducting, some current will flow here and the overall load resistance has decreased. So the current here will increase, isn't it? And when the overall load resistance decreases, the output voltage will be lesser than given by this formula. So the voltage given by this formula was increasing this way, but now it will be less than that. So the graph will slightly come down. So the slope will decrease. So this is also called knee, Knee, okay? So the graph will have a slightly less slope now, and then when it becomes 6 volt, why 6 volt? Because you have one more diode here, isn't it? So when you voltage across P and Q, which also means voltage across these 2 points, right? P and this point has same potential, Q and this point has same potential. So when this voltage becomes slightly greater than 6 volt, now this diode will start conducting. And once this diode starts conducting, voltage here should remain constant at 6 volt, meaning this voltage, which is your output voltage, will remain constant at 6 volt. Okay, so the graph will go like this, right? Now, if you are happy with the answer given, then it's okay. But if you really want to know why the slope of output voltage versus time graph, why that slope decreases when this diode is on, if you really want to see mathematically, then let us do the details of this problem. For simplicity, I've assumed these resistances as R1, R2 and R3. And we know when the voltage here between P and Q is less than Zener voltage for this diode, which is 4 volt, then we know both are off, so no current will flow here or here, so this resistance is useless. So the output voltage will be current in the circuit, and current will be input voltage divided by total resistance of this circuit will be R1 plus R3, this is the current, into resistance of this load, which is R3. So that would be your output voltage. And they told input voltage varies linearly with time, so it will be equal to some constant into time. If you substitute this here, you will get KR3 by R1 plus R3 times T. So you can see this is the slope of your voltage versus time graph. This equation is like y equal to mx. So try to remember that when these diodes are off, that time the slope, let me call it m1, is equals to kr3 by r1 plus r3. Okay. Now let's see what happens when the voltage becomes slightly greater than 4 volt. You know this diode will be still off, so let us remove this diode. But now this diode will be on. So now current will flow here. So what will be the formula for voltage now? Let us try to think. So this is for case 1. Okay. Let's discuss case 2 here. Now let's say this point has some voltage, let us call it Vx. And this point, let us first assume all these points are equipotential, right? This is a single conductor, so all points will be at same potential. So 0 volt, this is also 0 volt, this is also 0 volt. This point is at Vx volt. This point will be same as this output voltage here, right? This potential difference is V0, so this point will be V0, this will be V0, and here this is 0, here potential difference is Vi, so this potential will be Vi. Now whatever current comes here, Is, that will divide here Iz, and some will go here Il, isn't it? And using Kirchhoff's current law at this node, what will you get? Is equals to Iz plus Il, right? Now Is is what? From Ohm's law, this current here will be potential difference for this resistor divided by resistance. What is potential difference here? Vi minus Vo divided, because this point is at Vo potential, right, which is same as output voltage. So potential difference here, Vi minus Vo divided by this resistance. What will be Iz? Well, this current here, you can see this is at 0 volt, and what will be potential of this point? Well, you know that this V0 and this 4 volt is potential difference here, which remains fixed, which is your Zener voltage. Let me write this as Zener voltage. So this potential difference will be V0 minus Vx is equals to 4 volt, which is Vz. So from here, if I take Vx this side, what will be Vx? V0 minus Vz, isn't it? So potential difference here is Vx minus 0 divided by this resistance, plus IL means current here. This current will be what? Potential difference here, which is V0 minus 0 divided by this resistance. And in place of Vx, I can substitute this V0 minus 4. In this case, it is Vz. Now, since I want output voltage, let me keep Vo together. Okay. So this will be Vi by R1 minus V0 by R1 equals to V0 by R2 minus Vz by R2 plus V0 by R3. Let me bring this Vz by R2 this side, so it will be Vi by R1 plus Vz by R2 equals to, I will take this one minus V0 by R1 this side, so V0 will be common, 1 by R1 plus 1 by R2 plus 1 by R3, isn't it? So your V0 will be equals to Vi by R1 plus Vz by R2 divided by 1 by R1 plus 1 by R2 plus 1 by R3. And you know that Vi is linear function of time, so it is Kt by R1. Let me write this one in this way, Vz by R2. So since you know this is constant, and R1 is also constant, K is constant, so this is also output voltage also is a linear function of time. What will be the slope of this equation? So this is your like y equal to mx plus this c. So this is your c, your y-intercept, and this is your, sorry, I became too over smart. So this will be your slope, isn't it? So the slope in the second case when the diode is on will be M2, let me write, will be K by R1 divided by 1 by R1 plus 1 by R2 plus 1 by R3. Now as I told, I need to show you that M2 is less than M1. So this has to be true. Now let us substitute and check whether this is a true equation or not. So M2 is K by R1 by 1 by R1 plus 1 by R2 plus 1 by R3 should be less than KR3 by R1 plus R3. K I can cancel. Then let me cross multiply this. So it will be 1 by R1 less than R3. Let me bring R1 plus R3 this side. R1 plus R3, and this one I cross multiply. 1 by R1 plus 1 by R2 plus 1 by R3. So here if I divide R1 by R1, I'll get 1 plus R3 by R1 less than R3 by R1 plus R3 by R2 plus R3 by R3 will be 1. This one and this one I can cancel. And this R3 by R2, if I bring this side, I'll get 0 by R3 by R1. And you know this is true only because these are positive values. Resistances are always positive, right? So since this is valid, 0 is obviously less than positive number. So since this is true, this is true. So that's why the slope of your output voltage versus time graph will be less in the second case when the diode is on.